Okay, guess we can get started. So I'll be talking about, I guess my official title is the security or insecurity of third-party iOS applications. I sometimes switch around. Basically, the idea is that what I'll be talking about is sort of well, I'll get that in a second. First of all, who am I? My name's Ilja. I work for a company called IOActive. I was part of a security research group called Metric, and I have a blog that I update once or twice a year. Um, So yeah, let's dive into what this talk is about and what it isn't about. Um, the talk is about common security issues that I've seen in third-party iOS applications. So iPad apps, iPhone apps that are written not part of the OS but written by third parties, right? I'll cover the common security issues that I've seen or noticed, and then I'll try to present some mitigations or fixes for the issues that I've run across. Um, and I'll document how to exploit some of these in some cases. What it isn't about is bugs in iOS itself. There's a fair number of iOS applications out there where people talk about the actual OS or how to jailbreak, those kind of things. I won't talk about that. To some extent, I will cover shortcomings of some APIs in iOS, but again, that affects third-party stuff, not the OS itself. Um, the mobile app market exploded a couple of years ago, when the iPhone came out and then you had Android, and then all of a sudden, you had hundreds of thousands of apps in these app stores written by all sorts of different developers and companies. Um, and I'd say about 2.5 years ago, we started getting customer demands from our customers, and I would imagine other security companies would get similar demands to review the mobile apps, specifically iOS apps. And at the time, there was very little known about it, security of iOS apps. I've done about 20 or so in the last 2 years, and basically this presentation is sort of my collection of notes of what I've learned in those 2 years, the common sort of issues I've seen among a large set of iOS applications, and things that I've seen iOS developers do wrong consistently. Yeah, so before we can dive into that, let's discuss the application environment for a second. iOS apps, almost all of them are native applications. What that means is they're written in Objective-C, which is this sort of offspring from the C language. It's a strict C superset. What that means is that every valid piece of C code is a valid piece of Objective-C code. It runs on iOS, which is basically sort of a port of macOS to the ARM CPU. I mean, there's a number of things that change, but essentially it's macOS on an ARM CPU. Interesting thing about Objective-C is that they offer a bunch of classes and methods and objects to take care of a lot of low-level issues, such as memory allocation, that kind of stuff. And we'll get back to that part in a little while. So the first thing I want to talk about is transport security in iOS apps. There are a large number of iOS apps that need to somehow securely communicate to a backend server or a web service or some kind of middleware. They tend to use SSL for that, and the way you do that is you basically create an NSURL connection object, and you pass it just a URL like you would do in your browser, https://, and then all this magic happens behind your back, and SSL happens, and all this communication happens. The thing is, there's a whole bunch of defaults in there that aren't quite as good as they should be, and so there's a list of default ciphers. And so if you just make this connection, you turn on a sniffer, you'll see something like this in Wireshark. And then if you look at some of the ciphers, I mean, you'll have the standard ones that are good, but then there's also a number of ciphers that are that pretty much suck, including export ciphers, 40-bit export ciphers, that kind of stuff. This is not the kind of stuff that you want to have on, but it's there. It's on by default. There's no documented way to turn it off, and it's actually documented that there's no documented way to turn it off. Apple Apple has a secure coding guideline, and in there, and I have the actually snippet here. They say, if you use secure transport for iOS, secure transport programming interface is not available. Use the CF networking interface instead. And CF networking does not allow you to change the cipher suits. So the problem with iOS is that the OpenSL APIs themselves aren't exposed, and there are a set of classes built on top of them. and they're not granular enough. They don't expose large functions of SSL functionality to developers. Um, and I mean, I can see that being, trying to make things easier on developers. But something like allowing you to set a cipher suit would be, I think, would be a great thing to export to users. I think developers should be able to do that. At the present time, they can't, which makes this kind of difficult because if you have the set of default weak cipher suits and you can't change it, then you can't really fix the issue. Um, but you can mitigate it. So you can say, I won't use Apple's, baked-in SSL library, and I'll take my own version of OpenSL, or I'll take, there are some other SSL libraries that are built for embedded stuff, like CYASL or MatrixSL, and you could use those. Another note on this, originally when I started doing these things, this was in iOS 3 and iOS 4, and they had these weak ciphers. Since then, I think Apple took note of this, and for iOS 5 and 6, they removed the weak ciphers, which is a good thing, but it's still, you still don't have the functionality. You can't add a cipher, you can't remove a cipher. It might be that, they took out these weak ones, but tomorrow someone will find, a vulnerability in one of the other cipher suits they expose, and you can't turn it off, right? So things are better now than they were 2 years ago, but you still don't have the functionality that you want. So when I had that snippet of the OpenSL, of the iOS secure programming guide, that Dr. Nathan said that the secure transport programming is not available. Use CF Network. And so I spent some time looking at CF Network, and CF Network also doesn't allow you to set these cipher suits. However, CF Network does allow you to do a few other things with SSL. It allows you to say that you will allow expired certs. It will allow you to say that you will allow expired roots. It will allow you to say that you will take any root. It will allow you to say that you don't validate the certificate chain. These are all things that are bad. They're off by default, but you can have code you can add code like this in your app, and this is perfectly valid. This will pass the App Store, where you can say allow expired certificates, allow expired root, allow any root, don't validate certificate chain. And if you have this piece of code, this piece in your code, you're kind of screwed. Luckily, this stuff isn't on by default. It takes a little bit of work for a developer to actually screw this up, but it happens because this is stuff you use for debugging, right? If I want to be able to sort of see my own SSL, the content of my own SSL traffic, this is the easiest way to do it, is to say, I'll take any cert and you just manually your own connection for testing, and you get to see, what the actual data looks like. And so I've had about 2 cases actually where people had this kind of code in their code, and there was a comment above saying, debug only, but they were about to ship, and their retail version still had this thing on it. So you raise this red flag and you say, make sure you remove this code before you ship. And I mean, there was I guess a paper about SSL that came out a week or so ago, which sort of said the same thing, where for the browser, SSL is pretty good, but when you look at non-browser type stuff like iOS apps, these kind of things are quite common, where people don't validate certificates. They don't, they allow expired roots and that kind of stuff. So this is I mean, very common, very much on topic. This stuff does happen. It's good that it's not on by default, but too many people either have it on for debugging or for whatever reason, and then forget to turn it off when they ship. So it's something that needs to be, if you're looking at an iOS app or if you're writing an iOS app, you need to keep this in mind. This is quite important stuff. Okay, moving on from there to URL handlers. So basically, when the iPhone came out initially, I guess when iPhone 2 came out, and we were allowed to make applications for the iPhone, there was sort of this decision made at Apple where they said, we're gonna have this very strict sandbox, and as part of this sandbox, we don't want apps talking to each other. And I mean, security-wise, that's kind of commendable to have these kind of very strict set of rules in place. But it's a little bit too strict, because sometimes developers want to have apps that talk to each other. Sometimes even, you'll have apps from 2 different companies that will want to share, some kind of data to have, some kind of collaboration going on. So this was, way too strict, and developers found a way around it. And what they did was basically, if you register your URL handler, anybody can call it, and so you can sort of use the URL handlers as an IPC mechanism between 2 apps. Initially, this was a hack found by developers, Later on, and certainly if you go to Apple's developer website now, it's a common practice. It's now accepted as a standard way of doing this stuff. But it wasn't there initially. It was a hack, and now Apple has sort of embraced it and supports it. The idea is quite simple. Any application can register a URL handler, and then another app can call that URL handler. It's a very simple IPC mechanism. I believe it was initially discovered or publicly documented by the people from Mobile Orchard. If you go to that URL, you'll see the original post about how to use URL handlers for IPC mechanism. Basically, the way it works is if you're making an app, you have a plist which describes a bunch of properties for your iOS app, and in that you can say, I'm going to use a URL handler, and my URL handler is going to be called, in this case, my protocol. And then code-wise, basically, it's quite simple as well. You just define a callback called handle open URL right here. And then the moment that URL handler gets called from anywhere, the OS sees it and says, oh, I know that's this particular application. I'll call that application and I'll call that handle open URL call back on that application. And this is all baked into iOS, the mechanism to do these things. Unforeseen consequences. Yeah, any web page can do that too. If you're browsing mobile Safari, you go to a web page, all of a sudden, this untrusted web page gets to call arbitrary applications on your iPhone and gets to pass it arbitrary arguments, which the application will not pass and thinks comes from another application. This is kind of bad, especially if you don't know about it and you're making this IPC mechanism and you go like, well, it's undocumented and I trust that the guy that calls me knows what he's doing, so I don't need to validate anything. And all of a sudden, you're parsing stuff that you think is trusted that comes from the internet. That's kind of bad. So, I mean, that in itself is bad. The other thing is, if you were to do this kind of attack, you would still need someone on their iPhone or iPad to browse a website and go to your website, and then only then do you get to write, JavaScript or HTML that gets to call into these URL handlers. Wouldn't it be neat if you could find a trick that automatically allows anybody from within from on your local LAN to just call these URLs? It turns out that there's a way to do this. As of iOS 3, there's this Wi-Fi hotspot feature in iPhones and iPads. And basically what that means is if you connect to a Wi-Fi network, the first thing they'll do is they'll go to www.apple.com. And if it comes back with a 302 response, some kind of redirect, iOS basically goes like, oh, well, this must be a Wi-Fi hotspot. I will pop up a browser window for you, and I will render this hotspot Wi-Fi page. This kind of looks like this. And so basically, if you can abuse this in the sense that if you knock an iPhone or an iPad off the local network, they'll try to reconnect, and then you could forge the 302 that goes to Apple and go, 302 to my local web server, and my local web server will host, this a piece of JavaScript code or HTML code that allows you to call into any URL handler. So it's sort of a way where you no longer have to trick someone into using mobile Safari. All that is required is for them to be on your network. This feature is on by default. You can't turn it off in iOS 3, but as of iOS 4 and beyond, you can turn it off, but it's on by default. So originally in iOS 2, iOS 3, this sort of hack was invented, and then as of iOS 4.2, what Apple did was they gave you a new set of API to sort of better support the IPC mechanisms of the URL handler. Prior to that, you had to call handle open URL. And now there's another callback called OpenURL, which is a newer one, and I would recommend using that one, using OpenURL over handle OpenURL, for two reasons. If you look at the documentation, you sort of get to pass different arguments to OpenURL than handle OpenURL. And the reason why I would recommend using OpenURL is because the API is much more elegant for IPC. You no longer have to do sort of serialization for your arguments. Because what you had to do with handle open URL was you had to form a URL and then do the question mark and then key 1 equals value 1 ampersand key 2, and so you have to serialize and deserialize all your arguments. Handle open URL allows you to basically pass objects back and forth, and iOS will do all the serialization and deserialization for you. So that absolves you of all these sort of parsing errors that would come with serialization and deserialization. That's one. The second one is that when that OpenURL callback gets called, you get to see which application called you. You get to see their application ID. And that's interesting because you can now build a whitelist or a blacklist of apps that you're going to allow that get to send data to you. So if you're going to use OpenURL as a IPC mechanism, you can have a whitelist and say, these 3 iOS apps with these IDs, I know these and they are allowed to talk to me and I will take their data. And if you're not one of these 3 app IDs, then I'm just not going to take your data. So it allows you to have sort of a whitelist of things, people that you want, or apps that you want to talk to and no one else gets to talk to it. So if you must do IPC on iOS apps, I would strongly urge using OpenURL over handle OpenURL. Moving on to WebViews. WebViews are sort of it's a class in iOS that allows you to embed a browser window into your iOS app. And people use it for 2 ways. Obviously, first one is, to use it as an actual browser, right? So you can browse and then go see web pages and so forth. But it's also commonly used not really as a browser, but sort of as a way to build up a GUI for your iOS app, because it's just, it's easy. If you have to build the actual iOS GUI, it's a little bit of effort. You have to fiddle with a few things, whereas if you just write HTML code, that's fairly easy. And obviously, if it runs HTML, it can do JavaScript, right? And so it's basically more or less of a window. So let's first look at UI views used as a GUI elements. Those are vulnerable to attack, right? They're vulnerable to cross-site scripting. If you build up your own HTML and you put, stuff in there that comes from an untrusted source, that comes from network, piece of like a username that comes over network or something like that. If you don't escape it properly, you are vulnerable to very trivial, very textbook cross-site scripting. So if an attack can inject unescaped data in there, you get cross-site scripting. Now, this kind of cross-site scripting, it's the same functionally than if you were to do it for a web app, except there's no cookies to steal. There's no session you can take over. It's just, local HTML in an iPhone app. So you would think it's not really all that exciting, except what a lot of developers will do is they will build, when they use a UI as a GUI, they'll build a JavaScript to Objective-C bridge. Now, by default, Apple has no support for a JavaScript to Objective-C bridge. I'm pretty sure they sort of said, I think that, my guess is that people at Apple said, we think that's a bad idea because of security considerations. And so what happened was, you have all of these sort of developer forums online for iOS apps and probably Android as well. And a bunch of people there basically said, we would like to have an Objective-C bridge. And if Apple doesn't provide one, we'll build one for you, and you can use this. And the way this was done is, if you have a UI web view, you can define a callback called should start loading with request. And what that means is if you have the rendered HTML and there's any kind of link in there and you click on it, it goes to this callback, and you get another URL back, and then you can deserialize that URL and sort of use that to implement a JavaScript to Objective-C bridge. It's different to compare to the URL handlers in the sense that the URL handler is global. It works for every app, for every window, for everything. Whereas for UI web view, you should start loading with request only works for that particular UI web view in that particular iOS app. So it's very much local, and it can only be triggered if you have a cross-site scripting bug inside the UI web view. But once you do have a cross-site scripting bug inside the UI web view, and you get the should start loading with request, and there is no JavaScript to Objective-C bridge, you have pretty much almost complete code execution. Once you have that, depending on what the URL handler implements, or depending on what this should start loading with request handler implements, you can do all these things that are implemented there from within JavaScript in a UI web view. So as I mentioned earlier, there's a bunch of these online communities for iOS development, and they'll have sample code, and a lot of the sample code basically does is like they'll take a JS call URL handler, and the first argument is a method to call, and the second up until the last argument are arguments to pass to the method to call. And this is one, and I found this on a bunch of these forums. This is pretty standard template code that was written by someone else, where they go like, if you want to build a JavaScript to Objective-C bridge, do exactly this. And then if you look at it, it's a JS call URL handler, and then the first thing they do is the first argument is the function, and then they go, oh, we'll make a selector out of that function, and then we call it. Um, if you have this in WebView and there's cross-site scripting in that WebView, you now get to call any function in Objective-C and get to pass it any argument that you would like, including pointers and that kind of stuff. So this can easily lead to complete code execution. That's if you use it as a GUI. Now, if you use it as a browser, there are still things you can do, or specifically, there is a large set of attack surface there that isn't generally there in a normal desktop browser, for example. It does a lot more than render HTML. It can actually parse a very large set of file formats, and it does it without user consent. So you go to a web page, and automatically, this thing can render a PDF file, or unzip a file, or render an Excel sheet, or render Keynote files, or do PowerPoint, or do pages, or this. And I think there's a few I didn't even have on there. So it's an enormously large set of file parsers. And one of the things we know about these file parsers is that, especially Word and Excel and PowerPoint, is that parsing those things securely is nearly impossible. Everyone has screwed it up. I mean, I think Microsoft's had over 100 advisories for Word, for Office parsing bugs. Apple's now had a bunch of them too in these parsers. So by just exposing all this attack surface, zero click without user interaction, that you are exposing an enormously large attack surface where there are bound to be many, many bugs. So we know they're enormously difficult to parse, and the fact that there isn't user consent is very worrisome to me. That's one. The second one is that what these parsers are, I mean, they're read-only in the sense that they're more conversions. So most of these basically get parsed, and then they get converted to HTML. And what happens is they get converted to HTML, but they get rendered in the current DOM. So that HTML now becomes part of the website that hosts it. So if any of these parsers have cross-site scripting issues, all of a sudden, you have an Excel sheet or whatnot that allows you to have cross-site scripting in a website. These are all Apple's APIs. This is all in proc. All this stuff is done by default. You can't turn it off. You can't go to UFView and say, no, I don't want you to support Excel sheets. It's just not there. I mean, if it's on by default, that's fine if Apple wants to do it. But the fact that there's no feature that allows you to turn it off, I find that worrisome. There's a few other things in there that it can do. For example, it'll detect phone numbers and turn them into sort of these telephone URL handlers. And if you click on them, the phone comes up in the iPhone, for example. This particular feature you can turn off, and if you don't need that, I would say turn it off. But that's only one small thing in the long list of attack surfaces that you can't turn off. So the only mitigation, because you can't turn it off and because it's on by default, the only mitigation that I could come up with is to render out of proc, to not use a web view. So, for example, the Facebook app has this thing where if you click on a link, they'll have their own web view that comes up, which is a browser and renders stuff, right? And then you have all this attack surface, which is within your own iOS app. And so the only mitigation I see there is to not do that. If you need to have a piece of HTML, is to call out to Safari and let Safari render it. It doesn't fix any problem. It just sort of shifts the blame, right? If somebody's going to exploit it, they'll get to exploit Safari and not your app. It's not great, but it's the best you can do within what the iPhone has to offer you. That's what at least I think that's the best thing you can do. So it's sort of, it doesn't fix any problem, but it sort of says, at least I won't be vulnerable, but it'll be Safari. Something that's fairly similar to the attack surface in WebViews or what they call UI image classes. And what UI image class is sort of it's a general image class in that it supports a very long list of images and it'll parse all of them. If you just point it to a link and it'll parse them, including all of these. And then there's some extensions to general extensions to some of these formats like EXIF and ICC. And it'll parse all of this stuff too as long as you point it to something. Again, that is enormous attack surface. And there's no way to say, go to UI image class and say, hey, the link I'm going to give you is a ping file, and you should only parse it as a ping file. It'll just you can send it something and say, assume it's a ping file, and really it's a bitmap file where you just happen to know that there's a bug in the bitmap parser inside of the iOS APIs. So the problem there is that the attack surface is just way too large for what you really want. I've come up with two possible. So you can't turn it off. It supports open by default. So there's no real fix. But I've come up with two workarounds that I think you can do. So one of the things UI image allows you to do is to use what they call the CG image reference, which is the core graphics library they use. And in core graphics is much more granular, where you can say, only open this JPEG file, only open this PNG file, only open a bitmap file. And if you go to core graphics and you say, open as a JPEG and it's a bitmap, core graphics will sort of bail out and say, yeah, I'm not doing that. So what you could do is use core graphics to open the image, and then you get a core graphics handle back, and that handle you can pass up to UI image, and then UI image will use that handle. That's one of the ways to do it. It's a little bit of effort because you have to sort of do core graphics to open the image instead of the UI image, but it's not that much work. The other thing you can do is sort of do your own little bit of validation before you pass things off to UI image. Usually the way it works with UI image is A, you give it a link to a piece of data, or B, you go fetch the piece of data, you put it in an NS data object, and then you pass that object to UI image. So you sort of put an intermediate step in there where you go fetch the data, you put it in NS data, and then before you pass it in NS data object to UI image, you go look at the first X number of bytes of the format. It's called the magic bytes, and pretty much any file format, and certainly any image format, the first X number of bytes tell you, hey, I'm a PNG file, hey, I'm a JPEG file, I'm a GIF file. So for example, these four, because they're quite common, if they start with these number of bytes, you can be pretty damn sure it's a PNG file. If it starts with these number of bytes, you can be pretty damn sure it's a GIF file. So you sort of at least try to close the attack surface where you say, before I hand the stuff off to UI image, I at least know that it's a PNG file and not anything else. So it's not really a bug, it's more the trying the closing of enormous attack surface. One of the other things that was very common that I've seen, and this isn't iOS specific, this is pretty much anything that uses any kind of web service or any kind of XML parsing or protocol where you send XML back and forth, could be vulnerable to this. But I've seen this in a lot of iOS apps as well. A lot of iOS apps basically end up being the sort of lightweight client for a web service or middleware, and quite often they'll talk XML to each other. And so you'll see these kind of XML injection attacks where a piece of data is sent to the iOS client, and then the iOS client extracts a username or an attribute or whatever from there, and then it takes that piece of data and sends it back to the service, and then when forming the request being sent to the server, they forget to do proper escaping of this piece of untrusted data, and all of a sudden you get XML injection. Whether or not, how bad the XML injection is depends on what your protocol does and what the protocol does and what it allows you to do. But it would allow you to basically inject entire pieces of XML into the XML being sent in. Equally the same thing for HTML headers. And this is actually quite common where basically it's the same process where you take a piece of data that comes from the service which you would consider untrusted, and then you send it back in some form back to the server as an HTML header or HTTP header, and then you forget to escape things like next line, and that would allow you to have header injections. Again, not iOS specific, but I've seen it in a lot of iOS apps, so I figured it would be useful to have it in there. So basically, this is a very simple example where you extract a file name that someone gave you, and you put on in your HTTP header, and you say take the file name, and there's no escaping. You just take the file name verbatim, you put it in there. And so if I can give you an untrusted file name, I basically put a couple next lines in there and arbitrarily inject HTTP headers and then also HTTP content. And again, depending upon what the service actually supports, this may or may not be, bad or not, right? It all depends upon the functionality the service exports to you. But this kind of header XML injection is rampant among iOS apps. There are a few good things though with regards to header injection. So iOS has some URLs to set headers. So if you don't just form them verbatim, but you use the actual APIs and objects for HTTP headers, basically the way it works is you build up this NS URL request or NS mutable URL request, and there are two methods on there: add value and set value. And basically you give a key and a value, and it'll do validation of the key and value. So if it detects that there's a next line in there, it won't actually send it through to the service side. So it's not vulnerable to injection. I'm pretty happy about that. I think that's okay. It's not perfect in the sense that when these methods detect a next line, they'll fail silently. So if there's a next line in there, it won't send any requests, but it won't be vulnerable to header injection either. So if you care about it failing, you sort of have to do your own checks for that. Also, it's not documented, so it's kind of a pain in the ass. I mean, as a developer, I'd be pretty upset about this. As a security guy, I'm okay with it. One of the things I've seen that are incredibly common among iOS apps are format string bugs. And this is pretty common to the C language type of things. And so what I said earlier is that so Objective-C is a strict superset of C, and that which is native code, but Objective-C offers a whole bunch of classes and objects that do all sorts of low-level stuff for you. And if you stick to the Objective-C classes and objects, you are not going to be vulnerable to stuff like buffer overflows and things like that. All of these low-level security issues that you have in C are technically still there in Objective-C, but if you stick to Objective-C objects, you can mostly avoid having any kind of those issues. Format string bug is sort of the exception, where you have these sort of low-level memory corruption bugs that Objective-C doesn't really offer a good alternative for. In fact, Objective-C offers format functions of themselves. And I think the reason why there's so many format string bugs in Objective-C apps is because most developers that end up writing iOS apps don't have a strict C background. They probably come more from the web services and web app. You know, they write Java code or PHP code or maybe C#, and they don't know the exact consequences of format string bugs or format string functions or the specifics of format string functions. And so it's if you don't know exactly how a format string function works, then you're easily going to have format string bugs. So obviously these format string functions can lead to format string bugs. So I've done about 20 reviews of iOS apps, and every single app I've looked at has had at least one format string bug. So the iOS developers don't seem to know about format string bugs. The vulnerable or potentially vulnerable Objective-C methods are sort of the list here. NSLog being one of the most common, but any one of these, if you use them the wrong way, you will have format string bugs. Since Objective-C is a C superset, it still supports the C functions and format functions. Printf, SNPrintf, fprintf, all of those are there. So a little note about exploiting these format string bugs. Usually when you where you try to exploit a format string bug, you would take advantage of the %n format specifier, which is the one that allows you to pop a pointer from the stack and write some data to it. And that totally works for these C format functions. It doesn't work for these because these are Objective-C specific format functions. And the format specifier parser in these Objective-C format functions doesn't support %n. So there's no %n. So when I stumbled upon this and I sort of found that there were all these format string bugs there, I was sort of wondering if there's no %n, how bad is it? If you can't actually write to memory, what can you still do? I mean, there's still %s, so you could leak memory. You could crash applications, but you couldn't actually get code execution. At least that's what I thought. And so what I did is I started looking at some of the Objective-C documentation, and they don't have %n, but they did add a new format specifier called %@. And if you look at the description, it says for the percent at sign format specifier says Objective-C object printed as string returned by description with local method, if available, or description method otherwise. Also works with CF type objects returning result of the CF copy description function. So what that basically means is if you call percent at sign, what it'll do is it'll pop a pointer from the stack. It'll see it as an NS object, and it'll call a function pointer on that NS object. So while you don't get percent %n anymore, and you don't get to write to arbitrary memory locations, what you get in return is you get to call arbitrary function pointers, which is equally bad, and maybe even a little bit worse, because you don't have to fiddle around with memory anymore. All you got to do is basically be like, hey, here, call this function. It's not exactly as simple as that. I mean, it's almost as simple as that, but there's still some parsing involved in terms of some parsing and validation of the NS object stuff. And so I started playing around with this in the iOS emulator. So I have some assembly in there, which is Intel assembly, to sort of see how easy it really is to exploit one of these format string bugs using percent at sign. And so basically, I don't. That looks good. I made a very, very, very trivial Objective-C application. Where, the main function, I give it an argument, and basically I do this NS log thing here, which is clearly vulnerable to a format string bug, right? And can be attacker controlled, and you have a format string bug right there. And so I run it in a debugger and see what comes out. And clearly, I get BBB, %x, which is the pop from the stack crap that was already there, %at sign, and then clearly you can see it crashes on 0x62, 82. So it popped something from the stack, and it parsed something, and it crashed on something in object message send. And then, basically crashed on the 0x62, 68. So somewhere in there parsed something, and then as of when it got from 62 to 82, it crashed on something. And I followed a bunch of these. It's very trivial assembly code, but I don't want to go over all of it. But I started following some of the assembly code and basically the parsing of this data that gets popped from the stack. And if you go into it a little bit, basically, you end up, this is the sort of, once you're inside parsing of this, in this object, at some point there's a structure for the function pointer. And once you go there, you end up in this function where eventually, a function pointer gets extracted and it gets just called. That's it. This was all I tested this stuff in the emulator, so I didn't actually do it on the phone, so it's not ARM. But from all I can tell is that things are fairly similar in ARM than they are in iOS. The structures are pretty much the same, and so the parsing is similar as well. And so you have to kind of fiddle around with these things, and you have to sort of build up a fake NS object stuff. And when I did all this stuff, I sort of said, try to basically sort of compact things into itself. So you have a very tiny piece of structure, which really isn't an NS object at all, but for the purpose of these format functions, it resembles an NS object close enough that you can get code execution out of it. And so when I jumped through all these hoops, I came up with this. And it basically, if you have to write an exploit for this, and basically write a piece of C code, and if you just randomly fill out the structure and then pass it on, and you have you pop the correct values from the stack, this should basically jump to the instruction pointer right here, more or less. Okay. Let's move away from forcing bugs. And so when I mentioned that about forcing bugs is that if you use Objective-C and you stick to the Objective-C classes, that you're mostly avoid having all these memory corruption bugs like buffer overflows and those kind of things. And that's true except for one particular thing, which is binary protocol handling. Objective-C has all these great classes for stuff like strings and integers and all sorts of things. But for binary data, all it has is data, which is basically sort of a pointer to a class which says, here's the length, here's a blob of data, and that's it, right? So if you end up writing or reviewing an iOS application that handles binary data, you're kind of stuck with that, and you have to fall back to C code. And once you start back going to C code, you have all these pointers with signed and unsigned ints and pointers to data and offsets and lengths and indexes in there. And you have to do all of these validation yourself. And as we know from years of bugs in C and C++ code, is that this stuff is hard to do, and that almost virtually everyone screws up binary protocol handling in C. And the same thing is true for iOS apps. If you do binary protocol handling in Objective-C, you have to fall back to C. You have to write C-style binary protocol handlers. And I haven't seen that many of them, but I've seen a few, and they're terrible. They're riddled with bugs, basically. So if you have to write a binary protocol handler for iOS, be very, very, very careful. One of the, other issues that I've come across, and again, this isn't iOS specific, but it affects iOS, is that you can have directory traversals. iOS has file APIs that are quite similar to Mac OS X, and so you're restricted to the sandbox, but the file system is still the file system, and it's still a directory hierarchical directory structure that you get to use. And for Objective-C, there's a class called NSFileManager that allows you to sort of, traverse directories and open files and close files and so forth. And so basically, the class traversal, I've seen a few of those when you use NSFileManager, which is basically if you take a piece of user data and you use that as a file name, then all of a sudden, you can use .. / reverse some of the directory and open a different file, or read or write a different file. And they happen. So this is something, if you're either auditing or writing an iOS app, something you need to look at is directory traversal. But what's really kind of cute about this stuff is that because you're using Objective-C and not really C, is that an NS string and a C string are not the same thing. So you can be vulnerable to poison nobite. So what that means is NS string is basically, it's a structure which says, points to a piece of data and says this is a string, and it has a length in there which says the string is this long, right? And so as long as you start using NS strings and use the Objective-C classes, strings don't have to be null terminated. They can just be a blob of data that you declare to be a string. But when you do this with file handling and you pass in a string along, eventually it goes from Objective-C to some wrapper that goes to the kernel, which is written in C code. And the way the kernel works is that it doesn't know about NS strings, and it just gets a pointer of data, and it goes up until the first null bytes it finds and says that's the string terminator. So Objective-C apps are incredibly vulnerable to poison null bytes when you try and do file handling. And so if you take the previous example, this one, and then you go there and you say, well, what we're going to do is we're going to tag on .extension so that whatever you do, it has to have this extension. And then if you're the attacker, you basically go like, okay, that's fine. But then as my last character in the file name that I give you, I put a null byte in there. And a null byte is fine for NS strings. NS string does not care about null bytes at all. But once it gets passed on the kernel, they'll see the null byte, and it truncates the extension. The extension goes away. In iOS apps, you have to be quite careful for poison null bytes when you're handling file names. As a sort of a last thing I want to cover is the XML parser, or the standard XML parser for iOS apps. It's called NS XML parser. It's not terribly, it's not great security-wise, but it ain't terribly bad either. One of the things it does is by default it handles DDTs, which is kind of bad, and opens up like billion laughs attacks. And there's no real way to turn off DDT parsing, which again isn't great. They don't resolve external entities by default, which is good. It can be turned on if you really want it to. So it's not great, but it ain't bad either. Basically, the way you sort of do, if you handle untrusted XML, the way you fix that is basically by implementing every DDT callout you can possibly have. So find an element with I did a list here. Basically, there's 6 for NS XML parser that you can find. And the way you sort of work around this is you declare every single one of them. And if they ever get called, you just abort. You go like, this is an untrusted piece of XML. You're doing DDT. I don't trust that. Fail, right? That's sort of how you fix it. So it's not great. It's hairy. It's error prone, but it's not terrible either. I would have preferred that index.xml had some kind of attribute where you could say, don't do DDTs. It doesn't have that. But I mean, the fix is basically to just implement all DDT parsers and say, if this DDT parser gets hit, then we just fail. Yeah, and I think I still have some time left, which is I went through the slide like faster than I thought, and this is pretty much all I had. Anybody have any questions? Okay, well, then thank you all for listening. It's been great talking here.